Hello everyone, I'm Zihao. It is my privilege here to present our work, remote keylogging in multi-user VR applications. So today we're going to show that how we've investigated that it is feasible to conduct remote keylogging attack in real-world VR applications. And this work is done in collaboration between UCSB and UCLA. So in the past few years, you may have seen very popular VR apps that pop up, like Rec Room, VR Chat, and Meta Horizon. So in these apps, you can virtually interact with strangers and socialize with them. And these apps already have millions to tens of millions of users. So through these apps, you may even have have a preliminary peek of what metaverse may look like, as you can, have parties, you can go to a concert, etc. And some people may believe that these social VR apps, or what we call multi-user VR apps, is the next big thing. But so in these VR apps, like typing is an essential way to interact with the app and with each other. And a user may type in various scenarios. So in this example, a user is typing a private message to their friend, or they may also type their password and other sensitive information, or they may also type in their credit card for some purchases. But did you know that your whole body movement can be seen by other users in the same virtual room? So the VR developers want to give you immersive experience, and they want the users to see each other move with their full body. But they didn't think about the fact that even when you're typing, this whole body movement is visible. Okay, so let's see this side-by-side comparison. So on the left, you can see a person is typing a message in Rec Room. And on the right, you can see that a bystander can actually see this movement very clearly. And just by looking, you may even be able to guess some character that this person is typing. So our goal in this paper is to ask, can we accurately reconstruct keys based on this typing movement? And the answer is yes. And next, I'm going to show you how we did it in real-world applications like Rec Room. So in this attack, we just assume the attacker to be just a legitimate user. So they just need to create an account like everyone else, and they just need to play the game. So if they first perform some experiments and basically just familiarize themselves with the game and know how the game works. For example, they want to know how the keyboard looks like in this game. And then when they do the attack, they just need to join any public room. And let's say in the room, there's a person that's typing. The server is going to broadcast this information to every other user, and that's why you can see the other user moving. And the attacker may just blend in and be one of them. So how exactly can the attacker exploit this? So next, let's have a closer look into the information flow between the attacker and the typing user. So when the user types, this movement input data is going to be synchronized to the server and then sent to the attacker device. And then the attacker game client, in this case Rec Room, is going to render that on the attacker's headset. So you can take the visual output and analyze that. Or in our case, we just take directly the game data that the game uses to render to directly extract all the precise location of everything. And then we just take this game data and reconstruct the keystroke from it. So in summary, our approach is basically just taking the game network update and do a sequence of extraction steps and reconstruct the keystroke from it. Okay, so first, let's say the attacker just uses a network traffic recorder like Wireshark and records a bunch of packets. And the first step is to extract out the relevant app packets, in this case, the Rec Room packets. And the attacker can easily do this by, for example, filter by the application app port. And now that we have the Rec Room specific packets, if we just, let's say, open one of the packets, we'll just see a bunch of bytes that we cannot understand just yet. So the next step is to parse it into all the fields that, just like how the game does it. And to do this, we reverse engineer the game binary and understand how exactly the game itself parses this data. But now that we have all the fields, like all the fields parsed, we still may ask, what do they mean? They don't mean anything just yet, and we cannot analyze them. So the next step is to extract the semantics and know exactly what each field means. And to do this, we basically reverse engineer the game further and understand how the input data ends up in the packet. So for example, item 2 here is just a vector, but what does it mean? Through this analysis, we can understand that, it actually means the position for the left hand. Okay, so now we have all the packets parsed and we end with the semantics extracted. So the next step is to just separate the packets into different players, just like how the game does it. And then for a given user, we have a bunch of packets, and we analyze the typing related events. And first, we find the packet that corresponds to when the user opens their keyboard, and we can extract the keyboard position because the keyboard position is going to be appearing in the fixed location right in front of user. And next, for each click, we're going to just extract where this click happens and which key it is pointing at. And after this step, we are able to reconstruct which keystroke the user has typed. Okay, so you may ask how effective is this attack? So we performed a user study with 20 participants, and we put the user and an attacker in the same virtual room and asked the participant to type a bunch of numbers, passwords, and sentences. And from our result, we can see that we can almost perfectly just extract all the characters correctly. And the percentages here represent the character-wise accuracy for the top 1, top 3, and top 5 predictions. And but you may ask, in the first experiment, it's just isolated between the user and the attacker. And does this attack still work if there's a lot of users? Can you still distinguish the keys? And second, the attacker may not be able to have the best angle on the typing user. So does the attacker work when the attacker cannot see the user? So we did another experiment with 2 users typing at the same time. And in this case, the attacker just faces the wall and doesn't see anything. And from our result, we see very similar accuracy, and the attack is not affected at all. And then you may ask, does this attack generalize across Rec Room, which is what we used for the first experiment? So to answer this question, we replicated the experiment on 3 additional applications, and we did it with 3 participants per app. And here we see very high accuracy, almost near perfect accuracy for the key reconstruction for all 3 apps, which means that the attack is generalizable. And further, you may say, reverse engineering takes time and takes work. So can we skip that? So if we add, so we tried to apply machine learning to skip this process, and we found that if we can have partial labels, keystroke labels for part of partial typing movement data, we can actually reconstruct the keys with a decent accuracy. And this works even if we're just feeding raw bytes from the packets into the machine learning model. So how do we defend against this scary attack? And common defense mechanism isn't going to be too ideal for this. So first, encrypting the network traffic is not enough because this data that we use to reconstruct a keystroke actually is used to render on the attacker's game client. So eventually it's sent to the attacker and then decrypted on the attacker's device. And the attacker can do all things they want to intercept this data. And secondly, if you add noise to all the movements, it comes with utility trade-offs. And like the avatar movements are gonna look a bit weirder, and it's gonna probably make the user experience a bit worse. So we need a better defense for this. So we propose to fully block the hand motion updates, specifically just doing typing, sensitive typing activities. And this needs to be done both on the applications and the OS level. So for application, it's pretty straightforward, and we need to block the typing. But for OS like SteamVR, they also provide overlaid system keyboard that you can use and type in each application. So we reported our attack to SteamVR, and all the applications were evaluated, and the attack has been acknowledged by SteamVR, Rec Room, and synced together. And furthermore, SteamVR and Rec Room has already created patches to fix this issue following our recommendation. So SteamVR has implemented a defense to stop sharing typing movement with the apps so that the apps cannot just show this movement to other users without knowing. And this has been, you can find this update in the SteamVR beta 2.7.1. And Rec Room has also implemented a similar defense to stop sharing sensitive typing movement. And you can also find this in their latest release note. And moreover, Rec Room has also rewarded us a bounty for our report. But still, we believe that more apps may still be vulnerable today. So we investigated, from our investigation, more than half of the apps offer typing functionality, and all of them just share this typing motion data with remote users. So, which makes them potentially vulnerable. Okay, so thanks for listening, and I'm happy to take questions.